Thank you so much, and greetings from Virginia to Turkey. I would, of course, love to be with you. Unfortunately, we have to do with a virtual format in my case. So I'm very pleased to present some work we've done over the past years on non-equilibrium relaxation and critical aging of flux lines. I won't have to explain to you what flux lines are, but I will explain to you what non-equilibrium relaxation and critical aging is. This work was done essentially by my student Harshvardhan Chaturvedi in his dissertation work. He's now moved on to work for Microsoft. And several other students were involved, also former students Hiba Assi, Ulrich Doper, Müsl, and Bart Brown, and my colleague at Virginia Tech, Michelle Plinding, who is an expert in aging. And this work was supported by the US Department of Energy. All right, to get us going, I would like to first talk a little bit about what physical aging is. Of course, if we are in an equilibrium state or in a non-equilibrium steady state, then all kinds of single time observables are time independent. That's the point of stationary. And 2-point observables, such as 2-point correlation functions, are only functions of time differences of the observables we're taking. However, if we prepare a interestingly nonlinear stochastic dynamical system in an initial state that is very far away from this steady state configuration, then we're breaking initially time translation invariance. So 2 time observables will actually depend on both times separately. And usually this kind of initial regime goes by fast if you have a fast relaxation time. So once we're beyond a typical system relaxation time, this goes away and we reach the stationary regime. However, if we have slow dynamics in the sense that we have a relaxation time that's much, much bigger than the kind of typical microscopic times, or even no finite relaxation time at all, namely algebraic behavior, power law decays, then this so-called transient time window becomes accessible both to experiments and to theoretical experiments. There is computer simulations and actually reveals some interesting features. So this has been long studied, for example, in coarsening dynamics, when you quench a system from a high temperature disordered state into an ordered regime. It's also very prominent at critical aging scaling, because we have power laws and infinite relaxation times due to critical slowing down. And it's very prominent in glassy kinetics, which you have in disordered magnet spin glasses and all kinds of things that have been topics in this conference. So that's the context of what we're doing. Once you are in this so-called transient time window where things depend on initial time, it turns out there are specific scaling laws that are relevant to this regime, which we call aging scaling laws. And one of the forms that these take is if I look at a 2-point correlation function, again of some observables, at 2 different times t and s, and at a distance x, then there is one exponent with one of these times. That's typically the earlier time. We call it the waiting time. That's described by an exponent small b. And then everything just depends, of course, on natural length scales. So the distance relative to some typical length scale in the system, and then maybe that length scale at these 2 different times in the ratio of these length scales at 2 different times. Now, often, but not invariably, you have these characteristic lengths, such as domain sizes, grow algebraically too. So like a power law with an exponent that's characterized by some dynamic exponent z. If that's the case, one can actually further simplify this general scaling law and put it in the form, if you look at the autocorrelation function, so at distance 0, same space point, then just this ratio enters, and if this ratio is governed by these power laws, it's really just the ratios of s and t that enter. So you get this, what is called simple scaling, where we have an overall exponent in front, and the correlation function really just depends on the ratio of these times t and s. So the later time t and the earlier time s. And this tends to be true when s is much bigger, both times are much bigger than the microscopic time, and t is also much bigger than s. So the observation time is much bigger than the waiting time. Also, if you go back to kind of this up above general scaling law, one can extract the asymptotic form for large times for this. And so by using simple scaling analysis and assuming this algebraic behavior, you see that at long times the decay should become a power law with a new exponent called this autocorrelation exponent and the dynamic exponent. So the question after writing down these scaling laws is, which you can derive them at critical scaling. So you quench a system from some disordered state to some critical point, and you can actually derive these and compute these exponents in an epsilon extension. But in general, it's not clear these exponents are universal. Are they corresponding scaling functions like the C-head universal, or are they actually characteristic of specific material properties? So in that case, they would be a nice characterization tool. And I would like to advertise these kind of studies to the experimentalists in the audience, because that's actually, again, another regime that is often accessible, sometimes even easier than a stationary regime, and can tell us quite a bit of non-trivial information about fluctuations and correlations in such macroscopic systems. All right, now let me just change gear and talk about the system under consideration here, which are type 2 superconductors and magnetic flux lines in them, as is pertinent to this session, of course. So we have a London penetration depth that is much bigger than the coherence length, and we have a negative interfacial free energy, so we're in the mixed state. And so depending on the external applied field, we have a given number of flux lines in the system. And what we're going to do is we're going to describe the system on a coarse-grained mesoscopic scale, where we actually ignore all the microscopic details and just view the system as a set of elastic lines that are mutually interacting and subject to pinning. So very similar to actually what we saw in the previous talk. Never mind, as we heard yesterday in Valerie's nice presentation, that Alexey Alexeyevich thought this idea of just using flux lines and treating them as elastic objects is silly. All right, so we are going to use this representation, and then we can write the elastic line tension in terms of the flux quantum, the penetration depth, and this log of the Ginzburg parameter. And then we have vortex repulsions, so that would, in equilibrium, in the absence of disorder, induce a triangular recursive lattice. And then we have thermal wandering, so we have some thermal noise in the background that would lead to creep, for example, as our chair mentioned in the earlier talk. And of course, at large temperatures, it would be flux liquid and dissipation. So we'd like to have material defects in the system to pin the flux lines and make this system usable. So following a standard, by now kind of old at this stage, representation in terms of an effective coarse-grained model, we are writing this, we're mapping the vortices on just trajectories, in our case 3-dimensional trajectories, 2-dimensional trajectories as function of the third dimension, which is along the magnetic field direction, so that's C. So those are elastic lines. Then we get these gradient terms here, which are really the elastic line tension. Then we have some pinning potential that I'll specify in the next slide, and we have mutual repulsive interactions, which we can switch on and off, and we'll look at both cases. And then really you should think of this in thermal equilibrium to be described by a grand canonical ensemble, where the number of flux lines is controlled by a chemical potential, and that chemical potential is related to the external magnetic field. On to the dynamics. As I said, we're going to look at some random disorder in our system that we throw about. In this talk, this will be uncorrelated point pins. And so we should be, once we're in a disorder-dominated state, in a vortex or Bragg glass phase. We don't have that many vortices, so we can actually really not in our simulations distinguish between those two cases. We look at a lot of defects though. So we have 1,000 of these point defects, and we describe them by some weakly attractive pinning potential, the precise shape of which doesn't really matter, but we like to choose this kind of smooth hyperbolic tangent function because it's nice numerically. And they can be weak, so it's only 0.5% of the elastic line tension that this pinning potential strength is. We discretize in the magnetic field direction, so we have about 100 layers. That would translate, once you put in numbers, to something like a separation of 35 angstrom, so roughly, keeping in mind we have layered superconductor such as IPCO. And we are acquiring some typical material parameters that we also steal from, or motivate from numbers known for IPCO, so they're listed here. And we are operating at low temperatures in these simulations. And then we're describing the system by a set of coupled over-damped Langevin equations for individual kind of flux line elements. Very similar again to Barbaro's talk previously given. And so there's a friction term in here, and to make that friction consistent in this kind of description, you really need to have some stochastic noise, which is thermal noise, and the strength of this noise is indeed just given by the friction coefficient in kT according to an Einstein relation. So we're assuming for these thermal random noise terms in this Langevin equation that this is described by equilibrium. That's a bit of an assumption, but you have to start somewhere. So the mean of these stochastic forces is 0, and their covariance is given by Kt and the friction term. So this is really just Bardeen, Stephen, viscous drag. And to answer the chair's earlier question, of course, you would get flux creep when you simulate this at sufficiently low temperatures. And then we have a relaxation term. We will just take this effective free energy we had on the previous slide, which contained vortex interactions and elastic line tension and pinning, and we just try to minimize that. So that's our systematic part in this Laurent equation. And then we have an overall driving force that we add to the system, which is assumed to be constant. And what this friction term is really doing for us in the simulation is sets a time scale. So as Barbara correctly said, ultimately this is all rescaled into effective time scales in the computer simulations. All right, so with this I can move on to describe some results. And the first bit is, let's just do a drive quench within the moving phase. So what we're going to do is we're going to set a fixed temperature, and we're going to take the driving current or driving force and let the system equilibrate, in a sense, find a non-equilibrium stationary driven state for a while, and then suddenly change this driving force to a different value. So the first bit we're doing, we're going to start in the moving vortex lattice phase. So we have a strong driving force that keeps the vortices depinned from these point effects, and they're actually reordering into a almost nice triangular moving vortex lattice. So this would be at very high driving forces. And then there is a critical depinning threshold. At some point when the driving force gets too low, the system freezes and enters this kind of Baraka vortex glass state. And so in this first set of numerical experiments, we're just going to suddenly switch the driving force from a large value, 0.035 in the units we're playing, to 0.025, but still above the critical depinning threshold. So the system actually remains in the moving vortex lattice state, but just changes its overall mean velocity. And so it's not fundamentally entering a different configuration. And therefore, you actually expect the system to quickly relax, exponentially relax to this new driven non-equilibrium steady state, and that's precisely what we observe. And since the relaxation is fast, we don't actually see aging. And so that is kind of shown in these plots here. We look at the 2-point correlation function for these vortex elements, and we just see how these follow in time, and we see that for very short waiting times, which is kind of this blue curve down here and the red curve kind of visible just above it, you see some aging. So this is not just a function of t minus s, but when the waiting time is sufficiently long, 13 and so on in our units, all these curves nicely collapse, which means we've reached the stationary non-equilibrium steady state. And then essentially we just see an exponential relaxation of this 2-point correlation function, and that's all as expected. And what I'm comparing here and in the following view graphs is non-interacting flux lines, where in our simulations we just shut off the vortex repulsion, and interacting flux lines where they're in the play. And you see a common theme also to be seen later, that the interacting flux lines actually relax faster, because you get collective relaxation events. Some flux lines try to relax and they just pull their neighbors with them to caging effects. And so interacting flux lines are always relaxing faster. And we see this already here. But no physical aging. So this is one regime where this interesting aging scaling regime does not show up. Next one, we're doing a quench from the moving into the pin state. So now we're starting a high vortex drive and suddenly switch to a vortex drive that will take us into the vortex glass regime. Actually, we just switch to 0, which is the easiest thing to do. And then as opposed to what we saw before, we see very strong distinctions between different waiting times. So you cannot just plot the system versus t minus s, and look for a stationary state. The system just hasn't reached a stationary state. Instead, it's actually decaying a lot slower, like a power law, not exponentially, and that just prevents the system from ever reaching this non-equilibrium stationary state. So there will always be dependence on both times, and in fact, as suggested by the simple aging scaling laws I was showing you initially, the dependence is really on t over s, plotted here in a logarithmic scale. So here we take the log of some waiting time to some power, which I called b before, multiplied with this correlation function, plotted versus log t over s. And then we see a nice collapse of these same data points that I have on the left, non-interacting and interacting bottom and top. And we see a nice data collapse at sufficiently large T over S that shows us this aging scaling works. We can extract this exponent B. It's quite small, but it's non-zero. It's 0.004 for non-interacting and 0.005 for the interacting case. And we can extract this other asymptotic power law decay law, which I defined before as autocorrelation exponent divided by dynamic exponent. So that's lambda C over Z. And that's 0.007 and 0.0011 respectively. Also quite small, but non-zero. So we can extract that, and we see that indeed these interactions matter. We're getting kind of different universality classes for these cases. All right, finally, in my remaining 5 or 7 minutes or something like that, I'd like to address critical quenches. So we're now going to start with an initial moving vortex lattice at high drive, and we'll suddenly switch down precisely to the critical depending force. And we're going to do this at different low temperatures, because at the actual depending threshold is, of course, a zero temperature non-equilibrium phase transition. So right at zero temperature, we get a non-analytic behavior of the system's response, which is the mean velocity of this vortex system as we are scanning through the drive. Right? It's like an order parameter goes like cusp curves in the grid. And so we see these kind of velocity force curves here, also obtained from our Langevin molecular dynamics simulations. And you see, for larger temperatures, this is kind of smooth, and for smaller temperatures, we reach this kind of onset. And then we also measure the gyration radius. So this is a measure of the transverse fluctuation of these vortex lines. We just kind of look how their mean deviates from the center of mass of the vortex line and look at the square of that, which in an infinite system, right at the transition, should be divergent. And indeed, we see a prominent maximum of this radius of gyration as we are crossing the depending threshold, which is somewhere here. That maximum depends on temperature, which is fine as it should, because again, the actual critical behavior happens at zero temperature. So temperature here actually plays a role very similar to actually finite size in usual critical phenomena. So we can do an analogy of finite size scaling, just doing finite temperature scaling. A similar possibility would be to view it as an external field. And so we have temperature as one relevant variable in the ionization group sense, and we have the deviation of the force, the driving force, from the critical driving force as the second relevant variable. And so with these two relevant variables, we can write down a two-parameter scaling law that is supposedly describing what happens near this non-equilibrium second order phase transition. So there's an exponent delta that describes the temperature behavior at zero, the deviation right at criticality. And there's an exponent beta over beta delta that describes the behavior as function of this driving, this reduced driving force F. And so that would be the definition of exponents for the mean velocity as shown in these graphs. And then these exponents here would just directly follow for the radius of gyration, which we assume plays the equivalent role of a correlation length. And it's a characteristic length scale that diverges, and so we give it an exponent mu. And so what is shown up here is again the same data on the left, shown again on the right, but now rescaled with these correct scaling exponents, and obtaining these rescaled plots from here and these rescaled plots actually from this drawing side on the left on this end allows us to extract these exponents, right? So from the left-hand side, to make this match, we can extract delta, and from down here we get the product beta delta, and so on and so forth. So we can actually extract these exponents and measure these critical indices, both for non-interacting and interacting flux lines, and compare them with a very nice similar scaling analysis that was done 3 years ago in this experimental paper published in PLB. And so this is what we're finding. And we see for the exponent beta, our numerical simulation for the interacting case matches nicely with the experiment. Others are a bit off. And the tricky thing, of course, in these is in our experiment, in our numerical experiments, we can tune very carefully that we're at the critical point and really be sure that we're not in a crossover regime where corrections to scaling are important. That's a bit more tricky in the experimental regime. So maybe that's an origin for these deviations, but of course we don't know. We can just report our data. And finally, we can look at critical aging. So we can look at a normalized, say, two-term flux line height autocorrelation function. So this is again the kind of local fluctuations of transverse fluctuations of our vortices relative to the center of mass or mean. And then try an aging scaling collapse with the scaling laws I was telling you about early on in this talk. And also from these dynamical data, extract the look at critical slowing down, so how relaxation times depend on the deviation from the critical depending threshold, and then extract these dynamical exponents. So the previous one were like, stationary dynamical exponents, and these are aging dynamical exponents, dynamical exponent C, B, and lambda C. And so here again, the raw data for non-interacting interacting flux lines for this two-point correlation function, properly normalized, versus T minus S. We see there's definitely critical aging going on. And then we collapse them by trying to find an exponent B for which that would work, and just plot these data now versus T minus S, but versus T over S. And then the asymptotic slope gives us that exponent lambda C over Z. And then we can also measure this relaxation time independently and get the exponent C from that as well. There are hyperscaling relations that were postulated in the literature, and you can compare with those, and everything works out quite nicely. So here are the exponent values that we're getting for non-interacting flux lines for this aging scaling exponent E here, for this autocorrelation exponent relative to the dynamic exponent, and then the dynamic exponent. And then we can combine these, measure Z independently, and therefore obtain what lambda C is. And we can get this theta and measure mu, and then obtain theta from this hyperscaling relation. And down here is a table that we published in PRB a year ago, and you see that these are results we're getting to a fairly good precision. To my knowledge, that's the first time these kind of dynamic exponents were actually measured numerically for the system, and that's our results. All right, with this I would like to conclude and leave ample time for questions, I believe. Yes, we have still 5 minutes. And so again, my first advertising would be that non-equilibrium relaxation and aging properties could be a nice materials characterization tool. For example, in the previous talk, Barbara was adding the Magnus force to the vortices, which in this talk we have neglected, but we have put that in, of course, when we talk about Spermian systems, they're very prominent. And so the Magnus force, for example, is changing the universality class of these systems. Certainly in quenches into ordered phases has a very prominent effect, and actually also accelerates relaxation processes. Then we saw this kind of very complex relaxation dynamics that we're studying in disordered type 2 superconductors. But the aging scaling regime allows us to extract universal properties and distinguish what is universal and what isn't. For example, vortex interactions lead to different universality classes. And there is certainly non-universal behavior by quenching into the glassy phase. So there the exponents really depend on things like the vortex density or magnetic field and temperature. Then I showed you that we can look at critical aging scaling, and that actually allows a very accurate measurement, actually superior to what you can do by accessing just the stationary regime of universal dynamic scaling exponents at the depending transition. And I would finally just mention that in ongoing work, we're looking at the depending transition of magnetic skyrmions in two-dimensional films. So these could be like point-like particles that you're driving, not lines. But there the Magnus force is important, as I said already, and it does actually accelerate the relaxation processes. So with this, I just have a list of pertinent references here, and I thank you all very much for your kind attention. And of course, I'm open for questions.
Great, thank you very much for your presentation. Yeah, it's very clear that the understanding whether these exponents are universal or they are material dependent is extremely important, especially for those of us who are experimentalists trying to interpret our results. Okay, so then I have a question. So when you're going from considering interacting versus non-interacting vortices, it seems like with your simulations right now, you're just turning it on or off, right? With your Langevin equation, right? So how should we think about really the transition between when vortices, when we need to consider our interactions and we don't? And how does disorder affect that?
Right, so experimentally what you would do, of course, is just look at a very dilute system, right? If your system is the typical distance between the vortices becomes much larger than the London penetration depth, then you're in a non-interacting regime, essentially. So what we could also do is just change that. We can't really change our number of vortices too much because we have computational limitations to that, but we could change lambda. So we could do this more, more continuously if that were needed. So if there were experimental questions to us, we could certainly run these type of simulations. I'm sure Barbara could do it at the end. But that's how you would think of this. While if you have a very dense system where the typical vortex distance is of the scale of lambda, then these interactions are important because as you know, the interaction are cut off exponentially at the scale of lambda. So that's really what it is. It's the density versus the penetration depth.
Okay, well then if you had a strongly disordered system, would this affect that?
Yeah.
Because I could imagine if you had a really clean crystal.
Right? So we actually have a strongly disordered system. We have weak pinning centers, but we have a lot of them. So we have on the scale of 16 flux lines, but we have 1,000 defects. Okay, so in that sense, once you're in the low temperature, low drive regime, it's definitely in a glassy, very disordered state. And as I was showing, once you have interactions switched on, relaxations are much faster, and that's because you get collective effects. It's not individual lines that have to find their optimal free energy, but it's collective, and so that actually accelerates relaxation. That wasn't entirely obvious to us before we ran this, but that's one of the main conclusions, that whenever you have these larger chunks, collective excitations really accelerate the relaxation processes.
So then have you seen any transitions, or can you model any transitions between your elastic flow regime and a more plastic regime?
So we have not looked into this so much because other people have, right? So if you look at what Charles and Cynthia Reichert have been doing,
at Lanel
very extensively, so they've done everything that. So we didn't need to just and do the same.
But at Lanel, the simulations those are molecular dynamic simulations where they're considering just point particles, right, and not flux lines. There's no Z, right?
Thanks so much. Yes, we do lines, and so we have actually done some of that, which too much to present in one talk, but we've done some of that for three-dimensional systems subject to planar defects.
Okay.
And then you get very interesting channeling effects and and commensurability effects and things like that. Absolutely.
Okay, great.
That's another talk, though.
Right. I'll email you about that.
Sounds good. Absolutely. Please do.
Thank you very much again for your talk.
Thank you. Thanks, everyone, and greetings to Twitter.